Alright, in this video we're going to look at how to use beta functions to evaluate some integrals. Some of these integrals will be improper, like B and C, and some are not, like D and E. So before we have a go at this, just going to remind ourselves some of the properties of beta functions that we're going to use. So the first one here, so the beta function of mn is equal to the gamma function of m times the gamma function of n divided by gamma function of m plus n. Of course, the beta function is defined by this integral here. And then the second one is the trigonometric definition of the beta function. And this one is connecting the beta function with this improper integral there. Alright, so let's get on with the first one. So in the first one, we've got the integral from 0 to 1 of x cubed times 1 minus x to the power 5 dx. So this could be evaluated by simply expanding. This can be evaluated by expanding and integrating. So if we expand this one, we're going to find 6 terms using the binomial theorem. So by expanding and then integrate term by term. We are not going to use that method. You can just work through it using that approach to confirm. We're going to use the fact that this is in the form of a standard. This is in the standard form of the beta function integral. So if you compare this with this integral here, m minus 1 is 3, so that means m is going to be 4, n minus 1 is 5, so n is 6. So this is the gamma function of 4 times the gamma function of 6 divided by the gamma function of 4 plus 6. Then the gamma function of 4 is 3 factorial, so it's 2 times 3. Gamma function of 6 is 5 factorial, 2 times 3 times 4 times 5. Gamma function of 10 is 9 factorial, 2 times 3 times 4 times 5 times 6 times 7 times 8 and times 9. So then we can cancel out here. 2 cancels out 3, 4, 3 goes 3 times here, 2 goes 4 times there, then 5 cancels out as well. So in the numerator we now have 1. In the denominator we have 12 times 42. So 12 times 42. So this is going to be 1 over it's going to be 1 over 504. So that's part A. I'm going to go to part B. part B, we've got the integral from 0 to 2 of t squared dt over the square root of 2 minus t. Again, this could be evaluated using u substitution. We are going to convert it into a standard beta function. So if we let this equal to I, what we're going to do is we're going to, so just looking at this and comparing it with the standard form, there are two problems we have. Standard form is integral from 0 to 1. Then we have got 1 minus x there. So the two problems we have is this limit and these two here. So what we can do, of course, is you notice that if you factorize the 2 there, then you can write this as 1 minus t over 2. So from that, we're going to let u be equal to t over 2. Alternatively, t is to u. So t squared is going to be 4u squared dt is going to be 2 du. And then when t is 0, u is going to be 0. When t is 2, u is going to be 1, which is now the standard beta function limits. So we're going to have in the numerator, we've got 4u squared 2 du. Then in the denominator, we're going to have the square root of 2 into 1 minus u. So the constants are going to be 8 on root 2, integral from 0 to 1, u squared. Then this term we can bring up to the numerator. And then this is now standard beta function. So 8 root 2 beta of 3 half, m minus 1 is 2, m is 3, and minus 1 is minus half, n is 1 half. So this is 8 over root 2 gamma of 3 times gamma of 1 half divided by gamma of 3.5. 3.5 is 7 on 2. Then the gamma of function of 3 is 2 factorial. Gamma function of 1 half is pi. The gamma function of 7 halves is 5 halves times 3 halves times 1 half times square root pi. So this is going to cancel out. Then if we tidy this up, in the numerator we're going to have 16 times 8. In the denominator we're going to have 15 root 2. This we can write as 64 root 2 all over 15. All right. Then in C, we have got the integral from 0 to infinity of dt over 1 plus t to the power 4. By the way, this integral in B is an improper integral, because even though the limits not infinite, this integrand is singular when t is equal to the upper limit, because this is going to give us square root of 0. However, even though that is the case, the integral works out fine and is bounded. All right. So in this number C, we're going to evaluate this using 3 methods. Some of them from first year calculus and others from complex analysis. All right, so first of all, we're going to use a trigonometric substitution. So we're going to use a trigonometric substitution here. This is going to be a somewhat clever substitution. It's not your standard trig substitution. So we notice that if we can make this tangent squared, then the denominator is going to work out to secant squared. So what we do is we let t to the power 4 be tangent squared theta. What this means is that t is going to be the square root of tangent theta. Mind you, so here it's just going to be the plus, not the minus, because when you take the square root, you get plus or minus. But we know from here that t is always positive, because it's varying between 0 and infinity. So it's just going to be the plus case there. Then dt, if we differentiate this, we're going to multiply by 1/2 and subtract 1, gives us that, and then derivative of tangent is secant squared, so that is going to be our dt. Then next the limits. So when t equals to 0, theta. So here, if we plug in t is equal to 0 here, so this thing is going to give us tangent is 0, so theta must be equal to 0. And then as t goes to infinity, the question is in the positive values of theta, when does tangent go to infinity? And you're going to remember that this is going to happen when theta is pi on 2. So that means the upper limit is now going to be pi on 2. Then our integral can be expressed as the integral from 0 to pi on 2. dt is secant squared theta d theta. We have 2 times square root of tangent theta here. Then in this denominator here we have 1 plus tangent squared theta, which is just secant squared theta. So what's going to happen is that this term is going to cancel out, and then we're going to write these the remaining term in terms of sines and cosines. So I've got square root tangent in the denominator, so that means it's sine over cosine. If we bring the cosine in the numerator, it's going to be cosine theta to the power half, sine theta to the power minus a half. And now this is now in the standard beta function, but it's the beta function of it's the beta function, it's the trigonometric expression of the beta function. Now notice that this is equal to 2. We have got a half, so if you divide by 4 on both sides, then it's telling us that this thing is going to be 1 over 4 beta of. Now if 2m minus 1 is 1/2, then m is going to be 3 over 4. And then if 2n minus 1 is negative half, then n is going to be 1 over 4. Now, because these two add up to 1, then it means we have this type of situation here where p is going to be, well, we can make p to be 1 over 4, or p we can make it to be 3 over 4. This is 3 over 4, then that's 1 over 4, which is 1 minus p. So p is 3 over 4, but the result works out exactly the same as if p is 1 over 4. So this is going to be pi over sine 3 pi over 4. But sine 3 pi over 4 is exactly the same as pi over 4, because sine in the second quadrant is positive, exactly the same as the angle with the same reference in the first quadrant. So this is 1 over 4 pi over sine pi over 4 is 1 over root 2. Oh, let's just write it as 1 over root 2 is good enough. 1 over root 2. So this thing is going to be pi root 2 over 4. So that's the value of that integral there using method 1. Okay, looks like this this video is going to have to be split into 2, because we still have like 2 methods to go here. Method 2, and this is only example number C. So in method 2, we are going to use the residue theorem from complex calculus. Okay, so from there we're going to recall that the value of this integral here, dt over 1 plus t to the power 4, so the value of this can be obtained by evaluating a complex integral, evaluating the contour integral, this one. So the integral of dz all over 1 plus z to the power 4. Now the residue theorem says the value of this integral is just going to be 2 pi I times the sum of the residues of the function f of z. So that just talk about the singularities before we talk about the residues. So the function f of z is the integrand of that contour integral. So it's going to be 1 over 1 plus z to the power 4. Now, the singularities of this complex function given by is going to be 4 of them. First one is going to be e to the I pi over 4. Then we're going to have e to the 3I pi over 4. So this one is in the first quadrant. This one is in the second quadrant. This one is in the third quadrant. E to the 5I pi over 4. And this one is in the fourth quadrant, 7I pi over 4. Now, the ones that are going to be relevant for our calculation are the ones in the upper half plane, which are only these ones. Okay, so these are in the upper half plane. So we need to work out the residues of this function at these two. Now, just a little result, you're going to recall that if f of z is a rational function, p of z divided by q of z, then the residue of f of z at z0, where z0 is a pole, is simply going to be given by p of z0 divided by q prime at z0. Okay, so in this case, this is a rational function. P is 1 and q is 1 plus z to the power 4. So what's going to happen is that the residue of f of z at z0 is going to be 1 over derivative of that denominator is 4z cubed. Then we are going to plug in z0. So it's going to be 1 over 4e to the 3I pi over 4. So 3I pi over 4 is this thing to the power 3. This we can rewrite as 1 over 4 e to the minus 3I pi over 4. If we take that thing to the numerator, moreover, if we factor out the negative here, then we can write that thing as negative. Maybe I'm going to have to explain that. We are going to write that as negative e to the pi I over 4 all over 4. The way that is going to work is this. So let's just comment, explain this. It's going to be minus 3I pi over 4. What we're going to do is multiply both numerator and denominator by e to the I pi. Now remember, e to the I pi is just negative 1. So the numerator, if we add these two, it's just going to be e to the pi I over 4, because this is simply 1 minus 3 on 4. And then this is simply negative 1. So that's how we go from here to there. Okay, then at the other singularity, so at z equal to z1, if we do the same process, this is going to be 9I pi over 4. But 9I pi over 4 is the same as just e to the I pi over 4, because there's 2I pi there, which is 1. And then this is just minus e to the I pi over 4. So these are the two residues in the upper half plane. Then we can round this up. So the integral, so therefore the required integral, which is from 0 to infinity, of dt over 1 plus t to the power of 4 is half of this integral, which we can obtain using the residue theorem. So this is going to be half into 2 pi I. Then we simply add up the singularities, the residues. So it's going to be e to the minus I pi on 4. Take away e to the I pi on 4, all divided by 4. Then this we can just manipulate a bit. If we take the I to the denominator and bring one of the 2's here outside, then this we can write as e to the I pi over 4 minus e to the minus I pi over 4. So we inherit a negative because we're taking I to the denominator. So as you will remember, I is the same as negative 1 over I. So that's why these two terms are now the other way around. This one was negative, it's now positive here. This is positive, it's now negative here. But then this is just sine pi on 4. And of course sine pi on 4 is root 2 over 2. So that's going to be pi root 2 over 4, which is exactly the same as we found before. Then in the last method, of course, this is these are examples in the chapter on beta functions. So we have to see how beta and gamma functions apply in evaluating this integral. So I've got integral from 0 to infinity dt 1 plus t to the power of 4. So all we want to do is we're going to want to make a substitution and rewrite this integral in this form. So in the denominator we want 1 plus t, but in this case it's already t to the power 4. So I'll make this one into a new variable u. So we'll let u be t to the power 4. So t is u to the power 1 over 4. Then dt is 1 over 4 u to the power minus 3 on 4 du. The limits are going to remain the same because as when t is 0, u is 0, as t goes to infinity, u is also going to go to infinity. So our integral is going to be 1 over 4 from here, u to the power of minus 3 over 4, integral from 0 to infinity of 1 plus u. Then we compare this with that integral there. So p minus 1 is negative 1 over 4, negative 3 over 4, so that means p is 1 over 4. So we can simply write this as pi over sine pi over 4. So this is going to be 1 over 4 pi over, this is 1 over root 2, so it's pi root 2 over 4. And you can see that using beta and gamma functions, this works out in like 3 lines. Okay, then let's go to D. In D we have got the integral from 0 to pi over 2 sine theta to the power 4 cosine theta to the power 3. This we can evaluate using trigonometric identities. We save a cosine here and then write everything else in terms of sine. We're going to use beta functions for our calculation. So if we compare with the trigonometric definition, then if m minus 2m minus 1 is 3, then m is going to be 4 over 2, which is 2. 2n minus 1 is 4, it's going to be 4 plus 1 over 2. It's going to be 5 halves. So then this is simply 1/2 gamma function of 2 times gamma function of 5 on 2. In the denominator we're going to have gamma function of 9 on 2. Then this is going to be gamma function of 2 is just 1 factorial. Gamma function of 5 on 2 is going to be 3 halves plus 1/2 times gamma function of half. This one is going to be 7 halves times 5 halves times 3 halves times 1/2 times gamma function of 1/2, which is going to be square root pi. So that's going to cancel out. That's going to cancel out. That is going to cancel out. Oh yeah, and that as well. And this is going to cancel out. So this is simply going to be 2 over 7 times 5, which is 35. All right. I think going to stop here with this video. So we've done up to D. Okay. Then in part 2 of this video, we're going to do the other 4. All right. Thanks for watching. Hopefully this video is helpful. You can subscribe to our channel so that you get notified whenever we post new material. Thank you.